Lesson: Comparative Analysis of Machine Learning Paradigms. Machine learning paradigms are foundational to artificial intelligence applications and offer a structured approach to developing algorithms that can learn from and make predictions based on data. Each paradigm provides unique methodologies, tools, and frameworks, allowing practitioners to address diverse real-world challenges effectively. Understanding the comparative aspects of these paradigms is essential for AI professionals aiming to enhance their proficiency and adapt to various scenarios in the AI landscape. The three primary paradigms in machine learning are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning involves training a model on a labeled dataset, meaning that each training example is paired with an output label. This paradigm is extensively used for classification and regression tasks. Tools like scikit-learn and TensorFlow provide comprehensive libraries for implementing supervised learning models. For instance, scikit-learn's ease of use and extensive documentation make it a favorite among practitioners for tasks such as predicting housing prices using regression algorithms. A practical approach to implementing supervised learning is to start with a clear definition of the problem and the dataset. Suppose a company wants to predict customer churn. The first step is to collect historical data on customer behavior, including features such as usage patterns and service tenure. Using a tool like scikit-learn, professionals can split the dataset into training and testing sets, ensuring the model's performance is evaluated accurately. After selecting an appropriate algorithm, such as a support vector machine or a decision tree, the model is trained on the training set. Hyperparameter tuning and cross-validation are crucial steps that can be performed using Grid Search CV in scikit-learn to optimize the model's accuracy and generalizability. Unsupervised learning, on the other hand, deals with unlabeled data and seeks to uncover hidden patterns or intrinsic structures within the data. Clustering and dimensionality reduction are common tasks under this paradigm. K-means clustering, available in scikit-learn, is a popular method for segmenting data into distinct groups based on similarity. For example, in market segmentation, businesses can use K-means to identify distinct customer groups based on purchasing behavior, allowing for more targeted marketing strategies. Dimensionality reduction techniques like principal component analysis help in reducing the complexity of data, making it easier to visualize and analyze. When implementing unsupervised learning, it is important to pre-process the data correctly. This includes scaling features and handling missing values. Once the data is prepared, a tool like TensorFlow can be used to implement more complex models, such as autoencoders for anomaly detection. Autoencoders learn a compressed representation of input data and can effectively highlight deviations from normal patterns, useful in fraud detection applications. Reinforcement learning is a paradigm where an agent learns to make decisions by interacting with an environment to maximize cumulative reward. Unlike supervised learning, RL does not rely on labeled data, but instead learns from the consequences of actions. Frameworks like OpenAI Gym provide a robust platform for developing and comparing RL algorithms. A classic example of reinforcement learning is training an agent to play a game like chess or Go, where the agent learns strategies through trial and error to improve its performance over time. To implement reinforcement learning, professionals start by defining the environment and the possible actions the agent can take. Using a framework like PyTorch, one can design a neural network model that approximates the Q-value function, which estimates the expected utility of actions in given states. Techniques such as Q-learning and policy gradients are implemented to train the agent. PyTorch's dynamic computation graph offers flexibility and efficiency, particularly in handling the backpropagation process during model training. Comparing these paradigms, each has distinct advantages and is suitable for different types of problems. Supervised learning is highly effective for well-defined tasks with ample labeled data, such as image recognition and natural language processing. Unsupervised learning is invaluable when the goal is to explore data and uncover unknown patterns without predefined labels, making it ideal for exploratory data analysis. Reinforcement learning, with its focus on decision-making and adaptability, excels in environments where learning through interaction is crucial, such as autonomous driving and robotics. However, real-world challenges often require hybrid approaches that combine elements from multiple paradigms. For example, semi-supervised learning, which leverages both labeled and unlabeled data, can improve model performance when labeled data is scarce. This approach is particularly useful in medical imaging, where acquiring labeled data is expensive and time-consuming. Transfer learning, another hybrid strategy, involves taking a pre-trained model developed for one task and adapting it to a related task. This technique is instrumental in reducing training times and improving performance, especially in domains with limited data. Moreover, the choice of paradigm and tools is influenced by factors such as computational resources, data availability, and the specific goals of a project. Cloud-based platforms like Google Cloud AI and Amazon SageMaker offer scalable solutions that integrate seamlessly with popular ML frameworks, providing professionals with the infrastructure needed to deploy models efficiently. These platforms enable the implementation of end-to-end ML workflows, from data preprocessing to model training and deployment, allowing for rapid experimentation and iteration. To ensure successful implementation of machine learning paradigms, practitioners must also focus on model evaluation and interpretability. Metrics such as accuracy, precision, recall, and F1 score are essential for assessing the performance of supervised learning models. In unsupervised learning, Silhouette Score and Davies-Bouldin Index offer insights into clustering quality. Reinforcement learning benefits from metrics like cumulative reward and policy improvement rate, which help gauge the agent's learning progress. Model interpretability tools such as LIME and SHAPE are crucial for understanding model predictions, especially in sectors like healthcare and finance, where transparency is paramount. These tools provide explanations for individual predictions, enabling practitioners to build trust in model outputs and ensure compliance with regulatory standards. In conclusion, the comparative analysis of machine learning paradigms reveals a rich landscape of methodologies and tools that cater to diverse problem domains. By leveraging frameworks like scikit-learn, TensorFlow, and PyTorch, professionals can implement these paradigms effectively to solve real-world challenges. Understanding the strengths and limitations of each paradigm and the contexts in which they excel is essential for AI practitioners seeking to enhance their expertise and drive innovation in their respective fields.